If Thomson's cathode ray tube experiment gave us the charge to mass ratio of the electron, and for that matter, gave us the electron, then it was Millikan's oil drop experiment that gave us the charge and the mass of the electron. Remember, charge to mass ratio led to the discovery of the electron, but that wasn't enough information for us. We wanted more. We always want more. Once we had the charge to mass ratio, we wanted the charge and the mass of the electron. Enter a guy named Robert Millikan. Sets up an experiment called the oil drop experiment, which basically consists of two charged parallel plates. We'll make the top one positive and the bottom one negative, although they could be reversed. It's not really a big deal. That, by the way, would require a power supply that would look like this, with a positive terminal there and a negative terminal there. And then what we do is inject tiny little microscopic oil droplets in between these plates. If you have cologne or perfume at home, you know that we can take a liquid and atomize it. By atomizing it, we don't mean that we're turning this liquid into little particles the size of atoms. Not literally. We're just turning this liquid into particles that are really, really small. That's kind of what we're doing with these oil droplets as well. We spray the oil droplets in between these charged plates through something that amounts to a perfume dispenser. It atomizes them. It makes them really, really small. Some of them may already be charged due to rubbing against each other or due to rubbing against the nozzle of the perfume dispenser or the atomizer. Some of them may not be charged. We may have to expose these oil droplets to X-rays to ionize them. It doesn't really matter how they become charged. Bottom line is these oil droplets, microscopic oil droplets that came from this atomizer or perfume dispenser, become charged. So we're going to look at what happens if they become negatively charged, and we're going to look at what happens if they become positively charged. In both cases, there's two forces acting on the oil droplets. Remember, we're talking about oil drops, not electrons here. Even though it's going to lead to the charge of an electron, these are not electrons. Can you tell me what one of the forces is that acts on these oil droplets? Tom, what's one of them? Yeah, there's an electric force. The electric force would act downwards on this one. Because remember, the electric field goes from positive to negative, and the force acts in the direction of the field. The electric force would act upwards on this one, opposite to the direction of the field. Or in other words, toward the positive plate. What other force acts here? What are the forces acting on these oil droplets? I don't see any kind of magnetic field, right? What other kind of field could we possibly have here? Besides something like a magnetic field? Oh, gravity. Gravity is going to cause a downward force on the negative particle, and it's going to cause a downward force on the positive particle. Now, the positive particle will accelerate in this field. And it'll accelerate pretty quickly because it's got two forces in the same direction. The negative particle may accelerate if one of these forces is bigger than the other, or it may not accelerate. If the two forces balance, then it will either be suspended or move up or down at a constant velocity. Okay, we're going to analyze in a few minutes what happens if the forces aren't balanced, if it accelerates. But for now, we're going to focus on what happens if the forces are balanced. If that's the case, then the charged particle is either going to be suspended or travel at a constant speed. We're going to set Fe equal to Fg. Now, this should remind you probably of the velocity selection chamber of the cathode ray tube, where Fe was equal to Fm. Not the same thing. Don't memorize what's equal to what, because then you're probably going to get confused between cathode ray tube and oil drop experiment. Think about what's going on in each situation. Okay, in the cathode ray tube, we had an electric field and a magnetic field, those two forces balanced. Here we have an electric field and a gravitational field, those two forces balanced. Okay, think logically through it. Don't memorize what's equal to what. Okay, let's sub in Q times E for electric force and mg for gravitational force. Rearrange this to solve for Q. We get mg over the electric field. Hey, look, we just solved for the charge. The charge of what? Charge of what? The charge of an electron? No, Mac? Yeah, that's exactly what it is. The charge of an oil drop. So what does that do for us? Well, Millikan would have repeated this experiment hundreds of times. And when he did, he would have found that the charge values that he got from that equation could have been something like 3.2 times 10 to the minus 18, 1.6 times 10 to the minus 19, 9.6 times 10 to the minus 19 coulombs. I don't know, 4.8 times 10 to the minus 17 coulombs, so on. He gets hundreds of different charges of hundreds of different oil drops, and he finds, here's the big thing, he finds that they're all multiples of this. They're all multiples of 1.6 times 10 to the minus 19, which tells him a couple of things. Firstly, it tells him that if he's done this 500, say, times, and he hasn't found anything smaller than that charge, then that's probably the smallest possible charge you can have, the elementary charge. And if you can't get a charge smaller than that, then the particle that is the smallest particle likely has that charge. Therefore, the charge of the electron will be equal to, well, Thomson already established that it was negative, then 1.6 times 10 to the minus 19 coulombs. So he's got the elementary charge, and he realizes that that must be the charge of the electron. Now, just as a little aside here, if Thomson already found the charge to mass ratio to be 1.76 times 10 to the 11, and now Millikan found the charge to be 1.6 times 10 to the minus 19, then combined, you could find the mass, right? Thomson found charge to mass. Millikan found charge. We can use both of their analyses combined to find the mass. Now we know a lot more about the electron. We know that it exists. We not only know the charge to mass ratio, but now we know the charge and the mass of the electron, of that first known subatomic particle. The second conclusion that Millikan drew was that charge is quantized. What does that mean? Well, you can have this number 1.6, or you can have 14 times that, or 7 times that, or 2 times that, but you can't have 3.5 times that. We talked about energy quantization back when we were talking about quantum theory, right? Photon theory. You can have this value, or you can have 2 or 3 or 4 times that, but you can't have anything in between. Charge is quantized as well. You can have 1.6 times 10 to the minus 19, or you can have 200 times that, or you can have 6 times that, or you can have 300 times that, but you can't have just any value of charge. It's either 1.6 or a whole number multiple of that, right? Notice we haven't analyzed the particles that are accelerating yet. We'll deal with that one in a few minutes, okay? But what I want to do first is a sample problem involving charges that aren't accelerating, involving a charge that's suspended. This is on page 763. It says, an oil drop that has this mass is suspended in an electric field that's acting this way, how many electrons has the oil drop gained or lost? Here's what I want you to do when you see a Millikan oil drop experiment problem. Draw a picture. Some of you don't like drawing pictures. Some of you like taking shortcuts. Some of you think you know more than I do about this. When I tell you to draw a picture, you say, no, I don't need to do that because I'm smarter than that. No, you're not. You think you are, some of you, but you're not. Trust me, draw a picture. If you don't draw the picture, honestly, you're likely to be able to find the number of electrons and likely to get it correct. But you will not be able to know whether the electrons have been gained or lost. Draw the picture. Here's the oil drop. Positive or negative? We don't know. It's suspended, which means if it's suspended, the forces have to balance each other. So we know that one force has to be up and one force has to be down. And we know the electric field is downward. Think back to your electricity unit. If you have an upward force in a downward field, what kind of particle is it, positive or negative? Negative, good. Christian, if I had a positive particle in a downward field, the force would be downward. A negative particle experiences an electric force opposite to the field. That's a negative particle, and as a result of that negative particle, we know that electrons must have been gained. How many? We don't know yet, but we know that it gained electrons to make it negative. You can't answer that question, not easily, without drawing the picture. The next part of it, you probably could, but not this part of it. All right, how many electrons is it gained or lost? So let's say Fe is equal to Fg since it's suspended, or QE is equal to Mg. Solve for Q, becomes Mg over E. We get 8.2 times 10 to the minus 15 times 9.81 and divided by the electric field of 1.0 times 10 to the 5. Let's see what we get here. Eight times 10 to the negative 19. What have we just found again? The charge of, Karen, a charge of what? Sorry? Oil drop, yeah, the charge of an oil drop. Not the charge of an electron, the charge of an oil drop. Which, I mean, we'd repeat this hundreds of times if we were trying to find the elementary charge. But knowing the elementary charge, knowing the charge of an electron, all we have to do is take this number here that we got for the total charge, divide it by the charge of one electron, and that's going to give me the number of electrons, which is 5. 5 electrons gained, because we know that the charge has to be negative as a result of the force being opposite to the field. So we're able to solve for the number of electrons without a picture. We're not able to determine whether it's gained or lost without a picture. Okay, draw the picture. And if the odd time you find you draw your picture and you didn't really need it, oh well. Okay, oh well. 9 times out of 10, you're going to need that picture to get some part of the answer. So just draw it every time. Have a look at those two questions, please, then on page 763. All right, let's have a look at question number 2 here. It says, what electric field will suspend an oil drop with a mass of 3.2 times 10 to the minus 14 kilograms? And the charge is plus 2 times the elementary charge. All right, what's the first thing we do? Probably draw a picture, right? Draw a picture. What do we know here? We have a positive charge that has a charge of a value of 3.2 times 10 to the minus 19 coulombs. We know that we have an electric force up and a gravitational force down. They have to be opposite in direction if it's going to be suspended. What else we got? We got the mass of it, right? The mass is 3.2 times 10 to the minus 14 kilograms. That's a little bit confusing, both 3.2. We're looking for E, the electric field. So let's say Fe. Oh, sorry, wait. Yeah, we're looking for the electric field, sorry. So we're saying Fe is equal to Fg. We're going to say Q times E is equal to M times G. And we're going to solve for E here. It becomes Mg over Q. Mathematically, this is a pretty straightforward question, right? M times G over Q. What does it give me? 9.8 times 10 to the 5, I guess. But that doesn't tell us whether it's up or down. We can see by the answer in the book that the answer is upwards, but how do we know that? Well, if we have a positive charge, which we're told that it is, and we have an upward force, then what do we know about the field? If it's positive, the force has to be in the same direction as the field. If it's negative, the force is opposite to the field. Because it's positive, these two things have to be the same direction, which means it's got to be an upward field. All right? Does that make sense, guys? All right. What do we know? What do we do if the charged particles aren't suspended or traveling at a constant speed? What do we do if they're accelerating? We know that this charged particle that has two forces acting downwards must accelerate. This charged particle that has a force acting upwards and a force acting downwards could accelerate depending upon the values of those fields or those forces. What do we do if one of these particles is accelerating? Let me give you a hint. If I put this up on my board next period for my Physics 20 class, they could tell me what to do next. There's your hint. You knew what to do next when you were in Physics 20. Even though you knew nothing about the oil drop experiment and you wouldn't know anything about the oil drop experiment for another year, you still knew what to do next. What comes next? In either one of these situations where we have two forces that don't balance each other, the next step is always the same. Whether we're talking about an elevator with a normal force and gravity, whether we're talking about vertical circular motion with a normal force and gravity, whether we're talking about one of those pulley problems that you did in grade in Physics 20, the next step is always the same. By the net force. The net force is equal to the sum of the forces. In this case, it's Fe plus Fg. Ma is equal to the sum of the forces. Look, in Physics 20, you could do this. This is where it would end in Physics 20 right now, but you could get this far. Let's actually replace Fe with Q times the electric field. And let's replace Fg with M times G. Sub in your numbers. Solve for charge again. It's a little bit harder to solve for charge now. As long as you have your numbers, you can do it. Careful about signs, though. This one's always going to be negative, right? Because it's downward gravity. This one could be upward or downward, negative or positive. Here it's positive, here it's negative. This one could be negative or positive as well, depending upon which way it accelerates. How do we know whether they're negative or positive? We draw the picture, right? We draw the picture. That's what we do every time. Draw the picture. Look at it. Positive, negative, negative, negative. Picture tells us whether it's negative or positive. Plug in your numbers, solve for whatever you're looking for. Probably going to be Q. Get 500 different values of Q. Elementary charge, charge is quantized. Same conclusion we draw. Let's do one more example. Page 764. This is a tiny plastic sphere. When I was in university, I did this experiment, this oil drop experiment. It was a nightmare. It was the worst physics experiment ever. It was messy because we used oil droplets as opposed to plastic spheres. It was difficult. It was hard to find, it was hard to isolate individual oil droplets and so on. I don't even remember, to be honest, after about 10 or 12 hours of working through this experiment, I don't even remember if we got results that we were supposed to get or not, which says something about the value of the activity, the lab that we did, when I don't remember what I got out of it. All I remember is how difficult the experiment was. Now you tend to, and if you go to university and perform this experiment, you probably use plastic spheres now, little latex or plastic spheres instead of oil droplets, which makes it much nicer than if you're using an oil, like actual oil drops. Still probably not pretty, but certainly a lot less messy. So you're performing this experiment in 2016 versus 1993, and you're isolating a single tiny plastic sphere instead of a single oil droplet. It's got a mass of 8.2 times 10 to the minus 15. It's placed in an electric field that's downward within a vacuum chamber. The sphere has 10 excess electrons on it. Is it going to accelerate? And if so, which direction? Here's my negative particle. How do I know it's negative? Yep. Yeah, good. I have 10 excess electrons. 1.6 times 10 to the negative 18 coulombs. We get an electric field that's downward. We have a force of gravity that's downwards. And we have an electric force that's upwards. It's not always upwards. How did I know in this case that it's upwards? How did I know here that the electric force is upward? Tom knows everything today, eh? Tom? Yep, good. Negative particle experiences a force opposite to the field. So we know it's upwards. All right, let's say F net is equal to the sum of the forces, Fe plus Fg. Let's say Ma is equal to Qe plus Mg. And then let's solve for A. If A works out to be 0, then it didn't accelerate. If it works out to be something, then it did accelerate. Mass is 8.2 times 10 to the minus 15. Solve for A. Q is 1.6 times 10 to the minus 18 times electric field of 1 times 10 to the 5. And mass is 8.2 times 9.81. We're going to make this a positive force because it's upwards, and this a negative force because it's downwards. Solve for A. Why did I draw the picture? So that I'd recognize that this was a positive value, not a negative value. Let's do the math here. Say 1.6 times 10 to the minus 18. Be careful with that. That would be a really common mistake in this question, actually, is to do what I just did. Just blindly type in 10 to the minus 19 times 1 times 10 to the 5. But subtract from that brackets 8.2 times 10 to the minus 15 times 9.81. And then let's divide that by 8.2 times 10 to the minus 15. 9.7. So does it accelerate? Yes, clearly it does. Which way? Up or down? Picture doesn't tell me here, it's just the sign of my acceleration. Jared, the sign of the acceleration is positive, so which way does it accelerate? If it's a positive acceleration, it's going to be upwards. All right? Is the diagram important? Yeah, it was, because that's what helped me with this. And if I get this opposite to what it should be, then I'm going to get the wrong answer here. Okay? Didn't help me to determine whether it's up or down, but I needed it to get to that point. All right. A couple questions to go with that, page 764. Just a note of caution, though. Both of these answers are incorrect. If you get the answer to question number 1 that they have, you're wrong. If you get the answer to question number 2 what they have, you're wrong. So you don't want the answers this time. This is we're entering the bizarro world where everything is opposite to what it should be. If you get the right answer, you're wrong. If you get the wrong answer, then you're probably right.